Have you ever wondered why time only moves forward and not backward? It may seem like a philosophical question, but it's actually deeply rooted in the science of thermodynamics, a branch of physics that deals with heat and temperature and their relation to energy and work. Let's consider a simple example. If you've ever dropped a glass and watched it shatter into 100 pieces, you've witnessed thermodynamics in action. The glass doesn't spontaneously reassemble itself, does it? This is because the laws of thermodynamics dictate a certain direction of time, from past to future, from order to disorder. Thermodynamics is not just about broken glasses, though. It's a fundamental part of our universe, governing everything from the steam rising from your morning coffee to the fusion reactions in the heart of the sun. It's the science that explains why engines work, why refrigerators cool, and why life as we know it can exist. The laws of thermodynamics are like the rules of the cosmic game we're all playing. They tell us what's possible and what's not, what can happen and what can never happen. They're not just abstract theories, but practical guides to understanding and manipulating the world around us. In this video, we'll be delving into these laws in a way that's easy to understand, even if you're not a physicist. We'll explore the fascinating world of thermal equilibrium, the principle of energy conservation, the intriguing concept of entropy, the absolute zero temperature, and the arrow of time. We'll see how these laws are not just dry scientific principles, but the very fabric of reality itself. They're the reason why we can remember the past but not the future, why we grow old, why we need to eat and breathe, why stars shine and galaxies form. So buckle up. We're about to embark on a grand adventure, a journey into the heart of the universe itself. And our guide on this journey, none other than the laws of thermodynamics themselves. Prepare for a journey into the heart of the universe, guided by the laws of thermodynamics. Imagine having 3 cups of water at different temperatures. Let's say the first cup is boiling hot, the second is lukewarm, and the third is freezing cold. Each of these cups represents a system, and each system has its own distinct temperature. Now, if we were to place these 3 cups in close proximity to each other, something interesting would begin to happen. Due to the nature of heat, which tends to flow from areas of high temperature to areas of low temperature, the heat from the hot cup of water will start to transfer to the colder ones. This is simply because heat is a form of energy, and energy, well, it likes to spread out. It's a bit like a crowd of people in a room. If everyone starts at one end, they'll naturally spread out to fill the entire space. So, back to our cups. The hot cup will start to cool down as it loses energy to its surroundings, and the cold cup will start to warm up as it gains energy from its surroundings. The lukewarm cup, being in the middle, will both gain and lose energy depending on whether it's closer to the hot cup or the cold one. This process continues until eventually all 3 cups reach the same temperature. They have achieved what we call thermal equilibrium. It's a state where the temperature across all systems is uniform. No more energy is transferred between the cups because there's no temperature difference to drive the heat flow. This might seem like a simple concept, but it's actually fundamental to our understanding of thermodynamics. It's so important, in fact, that it's known as the zeroth law of thermodynamics. You might wonder why it's called the zeroth and not, say, the first or the second. Well, that's because this law was actually articulated after the first and second laws of thermodynamics were established. But it was realized that this law is so basic, so fundamental, that it should come before the others. Hence, it was assigned the number 0. So what exactly does the zeroth law say? In simple terms, it states that if 2 systems are each in thermal equilibrium with a third system, then they must be in thermal equilibrium with each other. In the case of our cups of water, if the hot cup and the cold cup each reach thermal equilibrium with the lukewarm cup, then they must also be in thermal equilibrium with each other. This law might seem self-evident, but it's actually a cornerstone of thermodynamics. It provides the foundation for the concept of temperature and enables us to measure it. Without the zeroth law, we wouldn't have thermometers, we wouldn't be able to determine the boiling point of water or the freezing point of ice, and we wouldn't have a clear understanding of how heat flows. The zeroth law also has profound implications for the natural world and for our everyday lives. It explains why your coffee cools down to room temperature if you leave it sitting on your desk, or why a warm pie cools down when taken out of the oven. It also explains why the Earth's climate system works to distribute heat evenly around the planet, and why our bodies work to maintain a constant internal temperature. In essence, the zeroth law is all about balance. It tells us that energy, in its ongoing quest to spread out, will continue to flow until it finds a state of equilibrium. It's a bit like a seesaw. If one side is heavier than the other, it will tip in that direction. But if you add or remove weight, it will eventually find a balance point where both sides are equal. That's thermal equilibrium. So the zeroth law introduces us to thermal equilibrium, where energy finds balance. It's a remarkably simple concept, but one that underpins our understanding of the universe and our place within it. It's a reminder that, in the grand scheme of things, everything seeks balance, even at the microscopic level of atoms and molecules. And this, my friends, is the beauty of thermodynamics. Behind every cup of coffee, every warm pie, and every gust of wind, there lies a world of energy and motion, seeking equilibrium, seeking balance. And it all starts with the zeroth law. So the next time you see a cup of coffee cooling on your desk, remember the invisible dance of energy happening right before your eyes. So the zeroth law introduces us to thermal equilibrium, where energy finds balance. Have you ever tried to create or destroy energy? Quite a thought, isn't it? Well, in our journey to understand the fascinating world of thermodynamics, we've reached a rather pivotal point, the first law of thermodynamics. This law tells us something quite profound, something that forms the very foundation of energy studies. It states that energy cannot be created or destroyed, but can only be transformed from one form to another. Picture this. You're at a theme park, strapped into your favorite roller coaster, the anticipation building as you slowly ascend that first towering hill. You're being pulled up by a mechanical system which is using electrical energy to do so. Now, as you reach the top and the coaster starts its thrilling descent, that stored potential energy transforms into kinetic energy, the energy of motion. That's the first law of thermodynamics in action, energy shifting from one form to another. Let's take another everyday example, something as simple as boiling water for your morning cup of tea. When you turn on the stove, you're using chemical energy stored in the gas or electrical energy from the grid, which is converted to heat energy. This heat energy then goes on to increase the kinetic energy of the water molecules, making them move faster and faster until they break free as steam. Again, no energy was created or destroyed, it simply changed forms. These transformations of energy are happening all around us all the time. The light bulb that illuminates your room, for instance, transforms electrical energy into light energy. The car you drive converts the chemical energy and fuel into mechanical energy to move the wheels. Even our own bodies are constantly transforming energy. When we eat, we consume the chemical energy stored in our food, which our bodies then convert into kinetic energy for movement, heat energy to keep us warm, and electrical energy for our nervous system to function. However, it's important to note that while energy cannot be created or destroyed, it can be wasted. In most energy transformations, some energy is often lost as heat due to inefficiencies in the process. Take the car example. Not all the chemical energy in the fuel goes into moving the car. A significant portion is lost as heat and sound. This is why energy conservation is so crucial. By optimizing our energy use, we can reduce wastage and make the most of the energy available to us. The first law of thermodynamics also has profound implications on a cosmic scale. It tells us that the total amount of energy in the universe is constant. From the moment of the Big Bang, no new energy has been created, nor has any been destroyed. All the energy that was there at the beginning of the universe is still here, just in different forms. It's been changing and transforming from light energy to kinetic energy, from kinetic energy to potential energy, and so on in an endless cosmic dance. So the next time you switch on a light, take a car ride, or even take a sip of your hot tea, remember, you're witnessing the first law of thermodynamics in action. You're seeing energy transform, but never disappear. It's a fundamental law of nature, and it's happening right before your eyes in the most ordinary and extraordinary ways. In essence, energy is the ultimate shapeshifter, always changing forms but never truly disappearing. It's there in every light and shadow, every sound and silence, every movement and stillness. It's there in the warmth of the sun and the chill of the wind, the rustle of the leaves and the roar of the waves, the beat of our hearts and the thoughts in our minds. It's the lifeblood of the universe, an eternal symphony of transformation. So let's take a moment to appreciate this amazing law of nature and the incredible universe it shapes. The next time you see energy in action, remember, it's not being created, It's not being destroyed, it's just changing forms. And that's the beauty of the first law of thermodynamics. Remember, energy is the ultimate shapeshifter, changing forms but never disappearing. Why does a hot cup of coffee cool down in a cold room, but never the other way around? This question takes us to the heart of the second law of thermodynamics, a principle that has profound implications for everything from the functioning of your refrigerator to the fate of the universe. The second law is all about a concept called entropy. Picture yourself with a deck of cards. You start to shuffle them. As you do, you'll find that the number of ways you can arrange those cards increases. In fact, there's an astronomically large number of possible arrangements. Now, suppose you're aiming for a specific order, say, all the cards arranged by suit and number. You could shuffle for your entire life and never reach that perfect order. Why? Because there are far more disorderly arrangements than orderly ones. This is the essence of entropy. It's a measure of disorder, or more technically, a measure of the number of ways you can rearrange the components of a system without changing the system's overall state. In the world of thermodynamics, entropy is a bit like the universe's accountant. It keeps track of the balance between order and disorder. And here's the kicker. The second law of thermodynamics states that in any closed system, the total amount of entropy can never decrease. It can only increase, or in some ideal cases, stay the same. When you pour that hot cup of coffee, the heat energy is concentrated in a small area. But as time goes on, that energy spreads out. It moves from the coffee to the air in the room, warming it slightly. The coffee cools down, the room heats up a bit, and the total amount of disorder, or entropy, increases. This is why the coffee never spontaneously heats up. To do so would require moving heat energy from the cooler room back into the hotter coffee, decreasing entropy. And that, according to the second law, is a no-go. But what about life? Living organisms seem to defy this tendency towards disorder. We grow, we develop, we create complex structures. Doesn't that violate the second law? Not at all. Remember, the second law applies to closed systems, and living organisms are anything but closed. We take in energy from our surroundings in the form of food, sunlight, and so on, and we release waste back into those surroundings. The energy we take in allows us to maintain and even increase order within our bodies. But the overall effect, when you consider the waste we produce and the energy we expend, is an increase in total entropy. Think about cleaning your room. You can spend hours organizing, creating a neat and orderly space, but in doing so, you're using energy, which increases the entropy in the rest of the universe. And if you stop cleaning, the room will naturally tend towards disorder. Clothes pile up, dust gathers, things get misplaced. This isn't just a reflection of our human tendency towards procrastination, it's a fundamental law of nature. Entropy also has profound implications for the universe as a whole. According to the second law, the universe is gradually moving towards a state of maximum entropy. This is sometimes called the heat death of the universe. In this far-off future, all the stars will have burned out, all matter will be evenly distributed, and there will be no more usable energy. Everything will be in a state of perfect disorder. But don't panic just yet. This heat death is still billions and billions of years in the future. And in the meantime, the increase in entropy is what drives the universe. It's why the sun shines, why rivers flow, why we can live and grow. Entropy isn't just about decay and disorder, it's also about change and transformation. In conclusion, entropy is a fundamental aspect of the second law of thermodynamics. It's a measure of disorder, and it's always increasing in any closed system. From a cup of coffee cooling down to the ultimate fate of the universe, entropy is at work. It's a subtle and often misunderstood concept, but it's one of the key ideas in understanding our universe. So the second law tells us that the universe favors a messy room over a tidy one. It's not just an excuse for not cleaning up, it's a fundamental principle of how the world works. And it's a reminder that, in a universe governed by entropy, change is the only constant. Have you ever thought about the coldest temperature possible? Let's dive into the fascinating concept of absolute zero and the third law of thermodynamics. The third law of thermodynamics is a fundamental principle in the world of physics. It states that as a system approaches absolute zero, all processes cease, and the entropy of the system reaches a minimum value. In other words, it's the law that governs the behavior of systems at the coldest temperatures imaginable. So what exactly is absolute zero? It's the theoretical temperature at which particles of matter would stop moving entirely. It's the rock bottom of temperatures, the point at which kinetic energy, the energy of movement, vanishes completely. In the Celsius scale, absolute zero is minus 273.15 degrees, while in the Fahrenheit scale, it's minus 459.67 degrees. But most commonly, we refer to absolute zero in the Kelvin scale as 0 Kelvin. It's important to understand that absolute zero is a theoretical limit, not a practically achievable point. It's like the speed of light. We can get closer and closer, but we can never quite reach it. The laws of quantum mechanics explain why this is the case. At absolute zero, atoms would be in their ground state, the lowest energy state possible. However, Heisenberg's uncertainty principle tells us that we can never know both the position and momentum of a particle with absolute certainty. If an atom were at absolute zero, we would know both its position and velocity, which would be zero, and this is forbidden by the uncertainty principle. The third law of thermodynamics also underpins the principle of the impossibility of a perfect refrigerator. The concept of a perfect refrigerator is one that can remove heat from a system without using any work or energy. But the third law tells us that's impossible. As a system approaches absolute zero, the amount of work required to remove further heat increases exponentially. This means that to reach absolute zero, an infinite amount of work would be required, an impossibility. This principle has profound implications for our understanding of efficiency and energy conservation. It tells us that there are inherent limits to the efficiency of any process or machine that involves heat transfer. No matter how technologically advanced we become, these are boundaries we cannot cross. It's a humbling reminder of the fundamental constraints that nature places on us. The third law of thermodynamics also impacts the world of quantum computing. At temperatures near absolute zero, quantum phenomena like superposition and entanglement become more pronounced, allowing quantum computers to perform complex calculations at incredible speeds. But the closer we get to absolute zero, the more energy we need to cool the system, reaffirming the third law's principle of the impossibility of a perfect refrigerator. In conclusion, the third law of thermodynamics and the concept of absolute zero serve as a foundation for understanding the fundamental limits of nature. They teach us about the behavior of systems at ultra-low temperatures, the inherent inefficiencies in heat transfer, and the unattainability of certain theoretical limits. They remind us that in the grand scheme of the universe, we are bound by the immutable laws of physics. So the next time you feel a chill in the winter air, spare a thought for the unreachable cold of absolute zero and the infinite work required to get there. Remember that no matter how advanced our science becomes, there are some boundaries we simply cannot cross. The third law teaches us that there are limits in nature that we simply cannot cross. Remember our initial question: why does time only move forward? The answer, believe it or not, lies in the laws of thermodynamics. Let's take a moment to revisit the second law of thermodynamics, which speaks to the concept of entropy. In simple terms, entropy is a measure of disorder or randomness in a system. According to this law, in an isolated system, entropy can only stay the same or increase, it never decreases. This implies a direction, a sort of arrow, if you will, that points from order to disorder, from past to future. Now let's connect the dots. Consider a cup of hot coffee sitting in a room. With time, the coffee cools down as it transfers heat to its surroundings until it reaches equilibrium. This is a one-way process. You'll never see a cup of coffee spontaneously heat up by drawing heat from its surroundings. This is entropy in action, and it's why time seems to move in one direction. The arrow of time is therefore a consequence of the second law of thermodynamics. It's a reflection of the universe's tendency to evolve towards states of higher disorder. When we remember something, we're recalling a state of lower entropy, and when we anticipate something, we're thinking about a state of higher entropy. This is why we remember the past but not the future. But what about the other laws of thermodynamics? Well, they too play a role. The first law, the law of energy conservation, ensures that the total energy in the universe remains constant, providing a stable backdrop against which time's arrow can play out. The third law, which speaks to absolute zero, sets a lower limit on entropy, ensuring that time's arrow doesn't reverse course. The laws of thermodynamics then not only explain energy and heat, but also the flow of time itself. So, what does all this mean for us in our daily lives? Well, the laws of thermodynamics are not just highbrow scientific principles meant for textbooks and lecture halls. They have profound implications in our everyday lives. Let's delve into how. Consider power generation. The steam pushing the turbines in a power plant, the photovoltaic cells soaking up the sun's energy, or the nuclear reactions in a power plant all operate on the principles of thermodynamics. It's the movement and transformation of heat and energy that make our modern lives possible. Take a moment and think about the device you're using to watch this video. Did you know that the functioning of your device, too, is governed by these laws? The electrical energy being converted into light and sound, the heat dissipated by your device, it's all thermodynamics in action. And it's not just man-made systems. The laws of thermodynamics are at play in the natural world as well. For instance, they govern the processes in our bodies. The food we eat is broken down and converted into energy, powering everything from our thoughts to our movements. Even the weather patterns we experience are a result of thermodynamics. The heat from the sun warms the Earth's surface, causing air and water to move and create weather patterns. The winds that blow, the rains that fall, the snow that blankets the land, they all trace their origins back to the laws of thermodynamics. And if you think about it, these laws even dictate the universe at large. The life cycle of stars, the expansion of the universe, and the very existence of black holes are all guided by the principles of thermodynamics. Whether we realize it or not, the laws of thermodynamics shape everything around us, from the smallest cell to the largest galaxy. These laws are the silent puppeteers, pulling the strings of the universe. From the energy in our bodies to the cosmic dances of galaxies, the laws of thermodynamics are inextricably woven into the fabric of our existence. They're not just scientific principles, they're the very rules of the game of life and the universe.